יש פעם שעברה הייתה מבלבלת?
מה?
הייתה גרוע.
אמת?
פעם שעברה היה נורא. זה הייתה פשוט כל פעם.
נכון. אז. אוקיי.
לא כל. זה הנושא של טנגל קטגורי והאיזון. זה קטגוריה חופשית. שמקיימת כל מיני תכונות הלוגיות. לפחות בתכונות האלה. זה פחות מבלט, זה יהיה יותר נכון. אנחנו נראה מה שיהיה בחול.
ונראה שהעירייה שלי יכולה...
העירייה שלי גם יהיה?
כן.
כאילו... ויש עוד מיוחד דוד?
כן, אבל הוא...
לא דוד, כן דוד?
כן. אבל הוא פשוט מאחר בכל מקרה.
טוב. אנחנו נתחיל.
מה?
אבל נדבר באנגלית כי הוא ביקש לומר שרוצה לראות את הוידאו. אוקיי. So last time I defined this tangle category. I don't remember how we called it, a tangle category, bow category, whatever. So a tangle category, and bow I think was symmetric. Yes, so tangle, which was kind of braided, was braided category, rigid category, very nice, and I claimed that it is a free category generated by one object. And this is all. And it is a braided monoidal rigid category. It has one nice object, point, yes, and the up, whatever, but it's not free. And I tried to convince you why it is free, so I said I will not prove it. They also will not prove it, so you can really check that I'm not wrong this time. I hope I'm not wrong this time. But the main thing that was that each time we have a diagram like in the tangle category, and something like this. No, this. Then we can try to assign to it a morphism. So if this is x, so here so each time we have arrows ups and downs, and we can write x times x times x times down. And then I can try to assign morphism. And the idea is that I use the multiplication, sorry, the evaluation, co-evaluation, and the body each time to. So the idea that I try to factor n diagram to simple pieces. This is one of the pieces, this is the other piece, this is the other piece, and this is co-evaluation, evaluation, and body. The other, for the other body, the other way around the body. So this doesn't really work. Why? So we can ask what we assign to a loop. And they said yes, we assign to a loop. We have x times, we have like the identity going to x times a star. Yeah, and then I want to use a co-evaluation. I want to make it back to a one. But you probably notice, and I think we even say something about it, that you cannot really put now co-evaluation because this is a right dual is co-evaluation of I think like one of the goals. So the co-evaluation should go from x star tensor x. So no problem. We put here the braiding. So we can define something. But you already see that this kind of wrong to say that this is attached to a loop. More correct to say that this is attached to figure eight. So of course topologically they're both the same. So we can say, okay, we will attach this to, but we can't really do it because topologically lots of other stuff is also the same. I can now do this twist any odd number of times. 101 times. So I will get something which is like very, very twisted loop. Okay, topologically it's still a loop. So it still should go to the same morphism, saying this is the dimension of x. But why? And it doesn't have to be the same number. And it's additional relation. So yes, we can impose additional conditions on our category and then we'll get a functor. But this kind of look at nature. And the reason is that in any monoidal category we have, not any, but in rich monoidal category we have left dual and the right dual. Any monoidal category can define them and the H categories that exist. And in braided monoidal category, both of them are isomorphic. And even both of the functors are isomorphic. So put together isomorphism between the functors x goes star and x goes. So these are isomorphic functors. But this isomorphism is not very good one. So one way you see it's not very good one, that you have two such isomorphism. The braiding from one side, the braiding from the other side. So it already gives you some feeling that something wrong here. And what I actually want to say is that this is not a monoidal isomorphism function. So if I have two monoidal functors, I can ask whether morphism between them is monoidal. So it has to like commute with the tensor structure. So we probably remember it, yes, if you have x tensor, we have f of x tensor y, if f is monoidal, because this is isomorphic, canonically meaning part of the structure of the monoidal structure of monoidal functor. But also, so now I have two functors, so g of x tensor y, which is not isomorphic to g of g of y. And now, if I have morphism between the functors, I have morphism here. But here I have different morphism that come from the tensor product. We want this diagram to be commuted. This is monoidal morphism between two functors. And now I want to say that the isomorphism between these two functors is not monoidal. But this doesn't make any sense because these two functors are not monoidal functors. The duality does not preserve the tensor product, it reverses the order of the tensor product. So this is not the way to usually say it. They say consider the isomorphism of between x to x dual dual. Okay, so x, so not this dual dual. So we always say the isomorphism like this. Left dual of the right dual is x. Canonically, it's very nice isomorphism. But in braided category, we also have isomorphism like this. X to x dual dual because the left duality is the same as I dual. Now x dual dual is already a monoidal function. And the braiding gives isomorphism from x to x dual dual, but this isomorphism is not monoidal. And this makes our life hard. So the idea is that you could have think about the loop differently. You can say x1 goes to x, go to x times x star. Now x goes to x star star. That star will change. And now we can use a co-evaluation. Sorry, it's evaluation, because now it's something star times something. So this is kind of what we actually want to map the loop. But the problem is that this functor, that this morphism is not monoidal. And so it's unreasonable to expect that it will give you anything. Yes.
And which morphism is not monoidal?
From this to this, so from x to x star star, there is isomorphism for x to x star star, but if you can split isomorphism functor, if you let x run, but it's not but it's not monoidal.
It's not.
It's not monoidal. Right. So the functor, it's isomorphism between the identity functor and the dual dual. Both of these functors are monoidal functors, but the morphism between them is not monoidal. So if you want to have a chance that this braid category will be universal object, like if you want it to be initial object in the category of monoidal categories, then you need to impose some additional structure on these monoidal categories, some monoidal isomorphism between identity and the functor that you want to extra. Which you give. And this isomorphism is different than the one given by the grading because it is monoidal and not. So the one that's given by the grading is in fact like anti-monoidal, yes. So if you no, maybe no, I don't know what anti-monoidal means in this case. Okay, let's ignore for now.
So if we have this additional structure, then what does it make this angle category?
That I would say in 7 moments. But okay, now I want to talk about. I just motivated that we want to have some additional structure in order to somehow relate to the tangle category. So if we have so this motivates the notion of pivotal rigid category. So rigid category is called pivotal if you have isomorphism like this, which is monoid. It's more or less to say that the left and the right dual are isomorphic, but in a monoidal way, but it's not clear what it means, so this is better to write less. So this is conflict. Now, since if we're talking about pivotal rigid category, sorry, pivotal braid category, so by definition, pivotal is something that's applied only for rigid, because we talk about duality. But if it's in addition braided, then we have two isomorphism from x to x star star. So two isomorphism between these two factors. One of them is a pivot, and the other is some bad isomorphism, which is not monoid. So we can take the ratio, and we get endomorphism of the identity factor.
Wait, how did we get this?
If our category is pivotal,
yes,
then we can take the ratio. Like first do the pivot, and then do the inverse of the braid, the isomorphism that is given by the braid. Or the other way around. Or the theta. You can do both. You get theta inverse. Yeah. So, but theta is not an arbitrary endomorphism of the identity functor. It's first of all, it's not monoidal, but it is something else. It's something that fixes the non-monoidality that we have here beta, which is the isomorphism that comes from the braiding, which is not monoidal. So it's something that fixes the non-monoidality of beta and make it into P. So you spell out what does it mean, and you get this nice relation. So let's see whether I can write it. We have x tensor y. So we can write here theta x. So theta x times theta y. And here we get x tensor y. So we have this endomorphism. And we can write the braid y tensor x. And here we can write theta x tensor y. And here, again, y tensor x. So up to, maybe I confuse these two guys, but I hope that not. And this diagram should be confused.
Can you please explain again this beta?
So x star is isomorphic to x left star. Why? Because x star, what is the definition of x star? So for the up to confusion with sides, yes. So you have the functor of multiplication with x star, and you have the functor with equation of x. these two functors have to be adjoint from certain side. And this is given by unit and co-unit, yes? So what's the definition of the other external? One definition is to say that these two functors have to be adjoint at this time from the other side. So these two functors also adjoint, but from the other. Another definition is to say that these two functors have to be adjoint from the same side as these. So either you change the sign of the adjunction, or you change the sign of the central. Why it is the same, you remember, because of the unit. And so to make two functor adjoint is the same as to make unit and co-unit, so evaluation and co-evaluation morphisms. And in our case, in the duality, the evaluation and co-evaluation just comes from evaluation from identity to x times x star and from x and and now we see that if these things stand on the left, it means that you first multiply, so you now want to multiply with this, yes? So it's first multiplying with x star and then multiplying with x. And here it's first multiplying with x star, and so for the left, you're first multiplying with x and then multiplying with x star. So it gives you evaluation and co-evaluation for one side of compositions of the factors. And if all the gadgets stands on the right, then it gives you evaluation and co-evaluation for the other composition of factors. So it gives you a junction from the different direction. Okay, so these two functors, in general, these two functors are adjoint if and only if these two functors with the same x star, and these two functors are adjoint from the other side. So in both of these cases, we will call x star left. Well, or the right way because it's the other. And if you do it to the other direction, if you put x star in the other direction, and the still adjoint in the same side like this, it means that it's a left. So the left and the right dual are isomorphic because this functor, and then you can just change the order of multiplication and using the braiding, and you get isomorphism between the left and the right dual. And in any category, any rigid category, you have isomorphism like this. So in braided monoidal category, you have isomorphism like this. So if your category is braided, you do have isomorphism like this. But it doesn't make it pivotal, because this isomorphism is not monoidal. If your category, if you are given additional structure of a monoidal isomorphism like this, then you call your category pivot. And it's kind of a reasonable structure to ask because this is something that hopefully will allow us to relate it to numbers. The broad point of view is so it never seemed to happen. Say it like this because it's not really work. We can make another change. I say it, you know. But I want to make you familiar with terminology because I was very confused with terminology when I was Googling it. So now I want you to know the word. So you have a pivotal structure, so this is isomorphism. And if you have such structure and you have braiding, then you can consider the ratio. And the ratio going to be this n-morphism of identity, which is not monoidal, but it is anti-monoidal in this sense, that this diagram is connected. So it's allow you to when you adjust. So monoidal means that on x times or y is just that these two things are just equal, and let's call it anti-monoidal. It means that these two things are not equal, but they are joined using the braid. So this is okay. So now we can forget about the pivotal structure and say, suppose I just given theta like this, and theta n-morphism of identity that satisfies this condition called the ribbon structure in a category, and sometimes it's called a balance structure.
What?
Balance structure.
Balance.
Yes, so the category we call it balanced if it's have a balanced function. And theta itself will be called the twist. We call it like endomorphism of each object, and the moment we'll see why it's easier to call it a twist. So a category together with a twist called balance or Regan. It's equivalent terminology. We type. So balanced maybe because it's kind of that you can balance the braid. The braid. So it's not symmetric, but it's so if it's symmetric, then you have like canonical balance structure or canonical twist, just identity. Because this is it clear? Yes. I think I didn't solve this, but I think for symmetric everything is very simple. But for braided, the fact that you have this balance means that it's a bit closer to being symmetric. That you still, so the braiding is maybe not identity, but you still, or it's square is not identity, but you still can try to balance it. Yes, and it's also called twist because it's something that you automorphism of each object separate, and they have to be somehow compatible with the code. And now notice that the notion of balanced structure is some of Ribbon structure or of a twist. It's something that you can do for any braided category. It doesn't have to be rigid. Yes? And the notion of pivotal, that's something that you can do for any rigid category. It doesn't have to be braided. Just if it's not braided, you don't have any item of it like this, but still you can ask to have additional structure. But if your category is both rigid and braided, then to give a pivotal structure and to give a ribbon structure is the same. Why? Because if you, we explained before that if you have P, then you can create theta. And also the other way around. If you have theta, then you can say, okay, you have beta, and then you apply theta. First you create theta, and then. So, so this is why in our world, if we already talk about the rigid monoidal braided category, then we can say ribbon or can say pivotal, and so we'll say ribbon. And now, wrong guess number 2 is that the tangle category is a free category and generated by one object and subject to the relations that it's whatever pivot, that it's ribbon, braided, rigid, monoidal. Why this is wrong? Yeah, first of all, I didn't say in what is a twist structure, what is a twist on tangle category. But let's say because that has twist. So first of all, on the single object, on the generated object, the twist is trivial. It's just identity. So you have to have theta from a point up, arrow up to arrow up. This is just identity morphism, meaning this. But it cannot be identity always, because if you look at this diagram, so here we put identity, here we put identity, then what will we get? We get that no, at some point I need to put the inverse braid probably. Yeah, I'm sorry. Here I should put the inverse braid. Then we get that the braid square is identity, which is wrong because it's not symmetrical. So, but in fact, we don't really have a choice. Once this is identity, so what happens when we do this? So the idea is that we want somehow to yeah, so this is a braided category. Okay, I will just tell you the answer and then we'll try to convince why it makes sense. So you rotate 2 pi, like 360 degrees. But you rotate the entire two strings. So you start with this, and now maybe it's good going to explain why it's called twist, you do rotation in 360 degrees and then go up. So you get twice the braiding. Yeah, okay, maybe this pendulum is in here. So if this is identity and the x and x now are the same as the trivial object, so this identity and this identity, and this is a twist. And now you want to go here, such as its diagonal will be commutative. So if this identity will get twice a twist, so here you have to go do twice a twist, twice a braiding. So you have to do twice a braiding to the other side. So okay, up to a sign. And then this is the theta of 2 points. And what happens for theta of many points? So you just take the some of them maybe points up, some of them maybe point down, maybe them gains up, and yeah. You take all these strings, you glue them on something rigid so it will not break down, then you twist them twice, 360 degrees, or twice, or one, but like a full twist, and then you can continue up. So it's important that you do it like not 800, not 180. So this will be wrong, yes, because then maybe then the pattern of the arrows will not, it will not be orthomorphism. Yeah, it will not get to the same object, it will get to a different object. But when you do 360, then you get the same object. So it is a nice twisted fatigue. A nice, sorry, bad ribbon balance. But it is not the free one. Why it's not the free one? Because it's a relation that we do not usually. So, yeah, okay, maybe before I need to say how we even try to map it. So how, when we have a diagram, how do we map it to to if we have a general category, balance the rigid, and we have a string diagram, how do we get maps in the category? And the idea is, so we have the evaluation, and we have the co-evaluation. But what was the problem before? That the evaluation only work in certain directions, so only work like this. And the co-evaluation only work in an opposite direction, only work like this. And this is why we couldn't really connect, yes? So, like, now we have maybe arrow like this that goes up here. And we want to understand what it is, the mathematics. So this arrow should give us a morphism between identity to x star times x. And we don't have the co-evaluations. Co-evaluation is made from identity to x times x star. But we do have the twist action. So what do? We have so the correct way is to do it like this. Okay, not wrong. So we have a map from identity to x times x star. And then we have a map from x times x star. The braiding map from x star times x. Before we say this is what we do, but this is not a good idea. And now we should make the twist to one of them. I think it's the second one. You just need to choose some convention. So I think equal 1, tensor that. So it seems that the reason is that you need to choose some convention that in fact you can't really do it, but you can choose something, and then for each diagram you will get a map between the power of x downstairs and the power of x upstairs. But now we want to show that if two diagrams are topologically equivalent, then they give the same map. And this is not correct. And the simplest example where it's not correct is this panel.
Can I just ask something?
Yes.
So we just want this map from 1 to x third times x to be
So it defines-
monoidal. So
To be monoidal, not doesn't really make sense because it's not magnitude functors, yes. But we kind of want it to come from monoidal component. Yes.
so that's why we have to take this composition
Yes.
to break it.
The braiding with the twist. So without the twist, we will not have. And you probably can also you can also express it using the pivotal structure. That's maybe. So the pivotal structure is say 1, 2, 1, 2, x. The pivot structure. So this is the same as x double star, star. And we wanted to get it here. Yeah, so this is probably the same as this double star. No, we need to use also the body. Yeah, let's ignore it. We better body. Okay, so why doesn't it? Yeah, probably. Why doesn't it work? So you have this diagram. This string diagram. And in the topological category, it has to be identical. In the Tanger category, it is identical homotopic just. But if you try to decompose it to pieces, what will you get? You will get x. And then you add rule, we start with x. Here you already have 3 objects. X, tensor, star. No, so tensor x, tensor x star. Now, here you have the braiding. X, tensor, x, tensor, star. But you switch these two guys like this, yes. And then you have the co-evaluation, so you're not allowed to do directly the co-evaluation, but braiding pivot and braiding twist and co-evaluation, so I just call it shortened co-evaluation. X. Yeah, maybe it's even easier with the pivots. With the pivots, you just say, and maybe I should say here. You can say with the pivot to 1 goes down x goes to x left out for x because of the field pivot. The pivot, one way to think about the example between the two varieties. Yes, so here we can say x tensor tensor x co-evaluation of the second two factors. No, what's it? Okay. Yeah, the output code. But it's here, it's roughly. So, I want. Never mind, forget about it. Let's do this way. So, here I did the evaluation, and here I did the co-evaluation, and the co-evaluation is from the other side, but since I have the pivot, I kind of don't worry. So overall, I got some non-trivial morphism of x.
How did you? What was the last step?
Is this co-evaluation? Sorry, evaluation. No, because I put the star on the other side, it's on the left dual. Oh, okay, dual, and then the co-evaluation is opposite and the. So I got an automorphism of x. And I can ask the question whether it is trivial in arbitrary category, and the answer is no. In fact, this is just the twist on x up to n, yes. So you can think about it as an exercise, probably a confusing one, but probably not hard, but long and confusing. Everything here is confusing now. So this is the twist. So if the twist on X is not trivial, then we cannot map this is a category of ribbons to and you cannot map the category of tangles to a given category with an object. So if you want to make a correct statement, the correct statement will be like this: that the category of tangles is a free-rigid monoidal ribbon category, a braided ribbon category, such that generated by one object on which the twist is identical.
You mean it is not free because
There is additional
it
relation.
should have been like this rank should have been.
This in this category of strings, this thing is identity. In category of tangles. But in general, it's not. So if you put additional conditions, then it's free subject to this condition. In fact, you could have seen just from the beginning when I just described what is the ribbon structure on the tangle category. I said that it's not always identity, it can't be always identity, but on the generating object on single string, it is identity. So how do we make it free? So we remember what actually the twist do in general, for general string, for general object in the tangle category. So we have several arrows. We say we rotate 360 degrees, the entire all the strings together. And when we rotate one of them, we just don't see this rotation. Like if it was an actual chord, then it would have been twisted all. So it kind of would change. Maybe if you do it too much, then you probably know with and if you have non-wireless headset, then you probably notice that once in some time you need to redo all this twist. So you take it out and then you should do the twist. So what is the correct answer? The correct answer is framed tangles. So what is framed tangles on the topological level? It's also like passes like this, it starts with points and go upstairs, but with additional structure of framing. What is framing? Is vector field which is not tangential, which is say orthogonal to the tangent. And you do it up to, of course, a motor. And then you see that when you take this structure and twist it 360 degrees, you get non-trivial framing. You get that the framing do this 360 rotation. 360 degree rotation. So then there are no relation. So at least you can hope that it will be free, and this is the actual theorem, and this category is free. Free category generated by one object.
Why does the vector field change?
Because if you twist it, so the twisting now is not identity, it's 300 degree rotation of every, like each time you have. Yeah, I forgot to say that. So we start with one arrow up, or down, which say the direction on the string, but also we need to know if it's framing. And say that the framing always goes to the right side. You can do more, but then we'll have much more objects, and they all will be isomorphic. So let's assume it's going to always to the right side. So if you start with the point, it will go up, and the framing go here, and you end with the point such framing. Now you have the identity, which is this thing, but you also have the twist, which is when the orthogonal vector change its angle gradually and do in the entire duration of the path, it do 360 degree rotation. And these are not isomorphic things. Yes, you cannot homotopically make one of them now if you want to preserve. So another way to visualize it is what they call ribbons, and this way the ribbon category called ribbon. So instead of saying just vectors, you just consider not one-dimensional thing that the string is not one dimensional, but it's two dimensional thing, which actually looks like a ribbon. Let's take. Wait. Ah, better. Yeah, so this is identity map, and if I rotate 360 degree, I get the twist. And now we'll see why I call it twist. And now you can ask what happens if you rotate 180 degrees. So that's the Mobius law. And this is not a twist because it's a map from two different objects. So because in ribbon category, so in the category of ribbons, so like instead of tangle single ribbon, so like frame tangle, you not only consider the two-dimensional thing as an object, you also put a direction thing here. But you can imagine that from this side, okay, here it's very easy to imagine because we have uncooked and uncooked. So this is made from the same object to itself, but this is just two different objects because once it goes to left, one goes to right. And you can't decompose them. So in this way, they prefer the frame language when you see the direction, not the ribbon language when you don't really see the direction, you need to edit. And so, but still the name is ribbon category, not frame. So you can think about the frame category, the frame tangle category, instead of tangles of lines, tangles of these ribbons that can also entangle one inside the other and twist themselves. But you have to remember the direction matter. You glue them together, the direction should fit, so you don't have to mistake of the model. Any questions? More confusing than the last time, but let's continue. Less confusing. So it's better not to lie. Yeah. Okay, so now I want to talk about top functions. But let's shift the break and then top functions. So we meet in 11:10. לא נראה כמובן. את יכולה? עכשיו טוב. עכשיו תורך?
אני יודעת שאילי זה שאמא שלי בקה בזה.
אבל זה כן משהו מאוד פופולרי בתורת ההצגות.
ומה עושים בתורת הקשרים?
מה, עושים עם תורת הקשרים או איזה שאלות אנשים שואלים בתורת הקשרים? כאילו שהרעיון שלהם נושא מאוד כזה יסודי, כן? זה נושא כאילו מאוד יסודי, המצד של קשר הוא מצד מאוד פשוט. יש שאלה שזה מגיע את כולה, במובן מסוים זו שאלה תמורה, זו שאלה גבולית, וניתן שני קשרים, נבחר לעשות אלגוריתם שבדק עושים או לא, לא בזמן שקיים היקום, או כל זמן דומה לזה, כן? אבל עדיין אפשר לשאול שאלות מזה, זה לא תורה או דורקולרית, או מסורתית, זה ממש מצחיק איך היא הופיעה במאה ה-19, רעיון של איזשהו פיתאי מאוד רציני, לא כל מפעיה, שקיווה שהוא יוכל להסביר ככה את הטבלה המחלוקות עד לפני מדלג, לא הבין שהאינדקסים הטבעיים, לא הטבלה המחלוקות, המיליון של היסודות, הם לא הבינו שהיסודות מודקסים באופן טבעי על ידי יסודות טבעיים, אפשר היה לסדר אותם לפי המסה, אבל לקח זמן להבין שיש משמעות בסדר, כן. הרעיון שלו היה שלכל קשר, יסוד, כנראה קשרים מסובכים ליסודות שכבר לא קיימים בטבע, זה היה מאוד יפה, ואז עניין צריך לתת קשרים, אז כשעניין שם. עכשיו יש לה שיעור עניין, דברים תיאוריה. אולי כן סוג של אותו רעיון, יכול להיות חשוב למציאות.
אתה יודע, פריים סטנדרט זה גורם לי לחשוב שהם דווקא יותר טבעיים.
אנגל?
כאילו אתה
אם
כזה
זה פיזי אמיתי, אז הוא לא באמת אנגל או פריים טנגל. אבל הוא גם לא באמת פריים טנגל, כי שם...
למה הוא בעצם לא...
לא, שם בכל זאת זה קצת שונה. זה חוט אמיתי, אם הוא באמת עגול, אז יש לו המון אוטומורפיזם. לא רק סיבוב ב-360, כל כמות של מעלה.
אוקיי.
זה בעיה של שבועות מטר, אפשר להגיד שהם שום דבר לא בצינם. יש חלוקה פשוט.
אפשר להגיד.
זה חוט לא עושים.
אני פשוט חושבת על זה שכשזה סופרים, זה לא אותו.
נכון, אני אומר, זה אפילו יותר גרוע, את יכולה לסובב אותו ב5 מעלות.
רמי, אתה לא עונה לי.
אוי ויי.
סתם, אני צריך לדעת מתי אתה מרצה ומה...
חשבת ש...
אם יש לך אילוצים בעצם, זאת השם.
יש לי אילוץ שאני לא יכול, שאני אהיה חייב לוותר עליו כדי הקורס הזה.
אני יודע, אני אצרות, זה לא שים לב, אני אתחפש את זה.
לא, אבל הקורס הוא חצי מזה 3 שעות, כן. וזהו, אני חשבתי שאני פשוט אהיה האחרון ואיפה שיש לי.
הדובר האחרון.
לא, האחרון שיגיד מתי הוא רוצה להרצות.
הבנתי.
ממש נשאר, אז אני...
בסדר, תודה. ואם אתה יכול לכתוב...
אני יכול לכתוב, אני אכתוב.
כותרת גם וזה, גם...
טוב, אני גם צריך להתחיל לדבר.
מה אתם מאמינים?
יש כנס, עוד כנסים.
שבלי נכון?
אם יכול להיות, זה הרצאות קולוקווים.
אוקיי.
לא, ספציפית, שום אחר. מכירה את כנסים?
אני מכירה את זה.
נפתח, בואו ספציפית. כשלקחת קורס עם הכנה...
זה הקנבסקי הזה?
כן. כן, כזה, כן, שמני.
לא, אני פשוט...
לא, סבוכי מעניין. היה ספר כזה, בעיות יהודיות, לא הבעיה היהודית, הבעיות יהודיות, כאילו מקרה, יודעת, שמעת עליו? שבמשך, כאילו, תקופה די ארוכה, את המדיניות של אוניברסיטאות ברוסיה לא לקחת יהודים, אבל זה לא הייתה מדיניות לגמרי פומבית. השיטה לעשות את זה הייתה פשוט, כן, להביא אותם למבחן ולשאול אותם שאלות יותר ויותר קשות, בדרך כלל מנסים להימנע מבעיות פתוחות. אז הם אספו את הבעיות האלה, שאלו את האנשים אחרי המבחן מה שאלו אותם. המבחנים שהיו בעל פה, שום דבר לא מתועד, הכל מתאים לגמרי לשיטה, ופרסמו את זה. פרסמו את זה בשביל להוכיח מה קורה, אבל זה גם בספר רפואת מתמטיקה, ממש קשה. עכשיו הם עשו עוד דברים שהמשטר לא אהב, הם היו שניים, והוא ועוד מישהי, אותם דרסו, כאילו החליט שנשמע לא להביא יותר טלוויזיה, פשוט דרוס את הנקודים, זה די ברור שהיה שלטון, ואותו שמו ל4 שנים, אולי לא ל4 שנים, שמו לכלא. תקופה אחת. סופר שואל, אפשר להיכנס לזה. וזהו, כאילו הוא היה פעיל הגיעה בתחום של מתמטיקה, הוא הלך פה מאוחר, הוא לא היה שם. הוא לא הצליח את זה. הוא מורה. כל מיני מסגרות שם. הוא למד שם מתמטיקה, אבל בתור יהודי, הוא היה בגיל שהיכול היה לעשות תואר שם. הוא יכול היה לעשות תורה, אני חושב, תואר שם אפשר לעשות. תורה שכבר היה בשלב אחר בחיים. שם. והוא לוקח היה מהמקימים של האוניברסיטה עצמית. הוא כן קידם מאוד את ההשכלת מתמטיקה הספציפית האלה שלא יכלו לקבל אותו באופן חוקי. וגם בארץ זה השכלה. גם בתוך זה הרבה, וגם אני אצלי בבית ספר שלהם. מאוד לא סתם בית ספר. כן, בכל מיני תחומים. אוקיי. So, now I want to talk about bialgebras, half-algebras, groups a little bit. So, what is bialgebra? So, we have the category of algebras. So, the category, is the opposite category to the category of algebra. So, we can start with the opposite category to the category of commutative algebras. This category is known. Commutative unital algebras, and you know that this category have a product. So algebras have coproduct, commutative unital algebras have coproduct, and algebras and the opposite category have a product, which is the tensor product. The tensor product is the product in the category of the opposite category to the category of commutative unital algebras, and then we can consider the group object in this category. Which means that we have a map from A to A that satisfies some axes. And this is very well-known object. So up to taking opposite category another time probably, it is algebraic group. Why? Because you remember that commutative or linear algebraic group. That commutative algebra is the same as fine algebraic variety, and so, but up to opposite category. So group object in a fine algebraic variety is algebraic. So this is a nice notion. Now you want to generalize this notion to the non-commutative group. So non-commutative algebras, you can still take the tensor product. It still will be an algebra. define it. You take tensor product over the base field, say C, and then you define product just by this A with A and B with B, and in particular A and B commute. And then you immediately understand that if A and B commute, it cannot be the coproduct. It cannot be freezing because in freezing A and B doesn't have to. So in the opposite category to the category of algebras, the tensor product is not the product. So we can like hope to define like non-commutative algebraic varieties, non-commutative geometry, just as the opposite category to non-commutative algebras. But this category maybe will have a product, but the product will be very, very complicated and very different from this tensor product. So this is not what we do. We say that we define a monoidal structure on the category of algebra, which is a tensor product. So it's not the product, it's not the coproduct, but it is tensor product, just monoidal structure. And in monoidal category, we can discuss the notion of group object, but usually it's called algebra object, which is defined in the same way. So what if we, I think we talked about that when we know the category C. So what is an algebra object? Is an object A together with a map from A tensor A to A that satisfies the same axiom for group. If not a group, like of semigroup. So it will be algebra object and not a group object. So this is called algebra object. So definition by algebra is algebra object in the category, the opposite category to the category of algebras. And okay, if I want to be more accurate, I probably say that the category of bi-algebra is the opposite of this category, because I want that morphisms will be just morphisms of algebras, which also gives morphism of bi-algebras. So it looks very confusing, but what does it actually mean? It means that we have algebra 8 together with the morphism, but not from A tensor A to A, because it is the opposite category, from A then to A tensor A, which is called the coproduct. And then there is diagram. So this coproduct have to be like compatible with the product, so it have to be homomorphism of algebras, and there are some compatibilities that are given by the tensor structure, and I just will write down what is the answer. Correctly. So we have A tensor A next to A, next to A, next to A. So this is the multiplication, this is the coproduct. And then this using twice the coproduct. A tensor A tensor A tensor A. And here we have A tensor A tensor A. And this is a copy from Wikipedia. We'll check it. It's actually followed from some natural axiom. So this is something we want to do. So here you just twist this to replace these two guys. The category of vector spaces and the category of algebras with is in symmetric category, so you don't need to worry about breaking, etc. And here you take just yes, so the definition that you will find written in many places that just you have a linear map like this, linear map like this, such that this diagram is commutative, and both M and delta define, so M defines structure of algebra and delta defines structure of coalgebra. Structure of algebra on vector spaces, you know what it is. Algebra. And the structure of coalgebra is basically algebra in the opposite category of vector spaces, so we take the same axioms, like the and this is bialgebra. And you can think about it as if, like, first attempt to do analog of the notion of algebraic group to what's called non-commutative geometry. So if algebraic geometry says that fine algebraic geometry, then fine variety is the same like algebras up to taking commutative algebras. You say, let's take non-commutative algebras and try to think about them as geometric objects. It might work, might not work. In general, it's not really works, so you don't really have a nice theory if you don't put additional conditions, but when you do, then it's okay. Okay. So at the first glance, it looks reasonable, but when you look at it a little bit better, you see, okay, this is just co-multiplication. With groups, you need to have a group structure. You need to have unit element, inverse element. So this should be analog of algebraic sum. So what is analog of a group? So you would expect that it just will be group object in the category of algebras. And this does not work. I didn't understand why it doesn't work, but every time you Google it, you see questions in Math Overflow, and people say it does not work. And so instead, they have.
Why does it work?
And considering group object in the category of algebras with respect to the monoidal structure and given by the tensor product. So what does work? There is a notion of, which is similar to the notion of group, but it does not satisfy the same axiom of antipode. And so this is the definition of Hopf algebras. So I will not give a full definition because at this point in the code we probably don't want to give all the details. But so I don't remember how you usually denote it. So you have that's what it's here from A to A. So by Hopf algebra, is by algebra and additional structure of a map from A to A that satisfies some conditions, basically that reverse the co-product. So maybe this I can write even. Yeah, you have A tensor A, you have antipode, and you have here antipode phi, E tensor phi, and maybe this is the only condition. We need to check what this is the only condition. And so this is called Hopf algebra. Why it makes sense? So let's go back to the example of algebraic group. If G is algebraic group, a finite algebraic group, then we have the ring of regular functions in G. This is an algebra, it's a product, but the group structure on G gives us additional structure here, a coalgebra structure. How does it work? We have the multiplication map from G times G to G. This gives map to the other direction from O of G to O of G times 1. And each time you have polynomial here, you can compose it with the multiplication map and get a polynomial P. And this is canonical isomorphic of P. So this is nice. Now, okay, and so this gives you a bialgebra structure because we have the algebra structure here, product, and the coalgebra structure given by this co-product. And what is an antipode? However, map from A to A.
Fine.
Yeah, so what will be fine in this case? This is what map of O of G to itself you have that relate to the fact that G has an inverse. So you have an inverse map from G to G. So you can get the map to the other direction for regular function of G to regular function of G. So you just change the variable. So this is not homomorphism. Yeah, of course I need to say it's also it satisfies this, but also satisfies further. Now I get more base. Yeah. Yeah, I think you need to have this. Yes, so this is homomorphism of algebras, but it's not homomorphism of coalgebras. It's not because inverse does not commute with the product. Change the order of the product, and this is like this condition here. I will check afterwards. But this is the first one. And this is the notion of function. Product, co-product, and anti. And what we can say, and we can think about Hopf algebra as analog of a group, which is not when the space itself is not commutative. So the ring of functions on the space is not commutative. This kind of weird thing from point of view of geometry, but from point of view of algebra, it makes sense, at least to some extent. So let's see examples. So all the examples will come from classical group theory, so they all will kind of be produced. But even if you start with classical group theory, it turns out that you can do things in two different ways, and then not always the algebra will be commutable, so there will be something like that. So let's start with a finite group. We're a finite group G, and now we have functions on G, function from G to C. And in fact, these have two product structure. You can just take element functions and multiply them points y, but you also have evolution. So it's not really bialgebra at the first glance, because it's twice algebra. Bialgebra is algebra and coalgebra together. And here, both of the structures are structure of algebra. But this is kind of artifact of the finiteness of the group, because when the group is finite, then you can intertwine, you can replace algebra with coalgebra. So let's do it. Let's consider the whole algebra structure. So we do the algebra structure, the usual community. See? And the coalgebra, what will be the map from C sub G to C of G of G? So coalgebra is algebra object in the category opposite to vector spaces with respect to the usual sense of structure. So it's just such a map. You know what is a map? It's just a pullback of the product. Just each time you have function G, you can map it to first perform product and then perform. So you have a co-product and you have an antipode, of course. Self F map first perform inverse, then perform F. And this is a Hopf algebra function. But since the group is finite, you can make everything from the other side. You can make you can consider so here multiplication is just n of f times g of f of x is going to be fx times g followed by multiplication. And this is a couplet. But since it is finite group, you can reverse the order of the plates. So you can define f, the product will be like M F G will be convolution. This is not commutative product, but the co-product will be commutative. What will be the co-product? Will be the stupid F maps to how do we call it? We want function G times G, so delta of F, so delta of F of X over Y is equal to 0 if X Y, and F of X if X. Just a function leave or only again. This kind of corresponds to the pointwise product. In what sense it corresponds? I think again by standard duality. Yes, if you consider functions and this map, I forgot. You said theta. This is the C of G. Then the C of G. And so if you have the product which is mapped from here to here, then the dual map, like the pointwise product, stupid product. So what does it mean? So you take function pair of functions here, consider the function G times G, and then restrict it to the diagonal. Then the dual map will start with function G. And what is the dual to restriction of the diagonal? It's just pushing with respect to the diagonal embedding. So you just consider functions which are supported in the diagonal, zero outside the diagonal, and the diagonal is your original function. So basically, both convolution and those two pictures are dual in the sense that if you take the product and co-product, you consider the dual map, because both of these things have according to scalar product in a form. Functions on G, you can just take in a form by multiplying and summing all the values, maybe divided by the number of elements of G if you want. So if you take the dual maps, the transpose map, and then you get from one picture to the other. So you got now two Hopf algebra structure.
Which dual map?
So multiplication map is a map from C of G times G to C of G. So the dual map going to go to the other direction. Co-multiplication map is map from here to here. The dual map going to the other direction. So if you have a Hopf algebra structure on G, you can take its dual and get Hopf algebra structure, a new Hopf algebra structure on G. So if you start with this picture, when you have standard multiplication and this co-multiplication, pullback of multiplication of elements, then the dual algebra structure will be this thing. So you will get convolution, which is a dual to this co-multiplication, and this stupid co-multiplication, which is a dual of this stupid. So you didn't get anything like good, I don't know, you didn't get anything which is really non-commutative, because here you have commutativity of product and here you have commutativity of co-product. But you did get an example of Hopf algebra where the product is not commutative. With this one. Well, it's convolution. So
How is it defined again?
So there are two vectors. If you have a map between two vector spaces and each of them have a scalar product, then you have a map to the other direction. Even it means scalar product in the like linear algebra sense without the complex conjugation, just be linear, not the general be linear. And I don't put enough. You can probably do it. So you have this procedure of taking duality. Now, if G is infinite group, but you still consider it as a discrete group, then you can still get something interesting here. C of G. So we can still consider convolutional functions, but not of all functions. Only finite supported functions. So if you have functions with finite support, then you have this big picture of convolution. And here, if you have finitely supported function, then you have this this procedure, this coproduct, which will be defined. Now here, you can do everything with all functions. You have multiplication, which you define pointwise, and commutative. But notice, do you have common? No. No, I don't know how to do quantification. If G is not finite, because I know how to do quantification from here to here, but if G is not finite, this I don't think is not correct. And okay, so I take my role. Yeah, so you have this picture for arbitrary group with finitely supported functions. You think just know. So this function. What? Then we need to start to discuss lots of stuff. I don't know. I would say this picture you probably want L1 function, so convolution is something that works well for L1 and not for L2 in general. And so a convolution of two L1 functions is another L1 function. And L2 functions. But okay, you can start to do it in topological settings and get a lot of interesting stuff. Okay, so here we have like two examples of commutative and co-commutative. And also we have the example of commutative Hopf algebra, which is not co-commutative, that comes from algebraic group. So we have C of G, and let's work this, which work for finite groups, and C with finite for G, which work for arbitrary group, but only this example. And you have O of G to work with algebraic group. And maybe the most fun, universal enveloping algebra of LG algebra. So, only you probably know what it is, not what is the Lie algebra, what universal enveloping algebra. And do you know what is the Lie algebra? Okay, then maybe after the class. But okay, we have this construction, but I can't say what is the product. What is the code? So the product you know here. Algebra, algebra, what is the component? What is my component? To G. Then the answer is like this. I will define it only on the generators, but it's not with this algebra. So element into the algebra, alpha G. Next to alpha tensor 1 plus 1. And this is, you can think about it like a version of this thing. So this thing says that you take the delta function, x, and map it to delta times delta. Yes? Yeah, I said it. No, sorry, this also does not make sense for general group. There we don't have, we of course don't have this element, this function is not function that has support. I don't know, if the group is assigned support, then everything will be so. So delta at x goes to delta x times delta at x. And now, if you think about the Lie algebra, some infinitesimal version of the group, then on the group, delta function at the point 1 will go to this function tensor itself. So, but how do you think about elements in the Lie algebra? It's not elements delta function at point 1. You can think about it as a difference delta of G delta of G plus very small element in the Lie algebra minus delta of G. Now, when you do this mapping, it's kind of deriving this diagonal. This is what you get. This is the intuition. So the universal enveloping algebra is again an example of something which is not commutative, but it is co-commutative. And since mapping is co-commutative, it's given when you change the first and second coordinates, you get just the same sum for the other direction. So neither of this example gives you something which is actually non-commutative in its code. It's not commutative in both sides. but this code. So what happened when you consider the category of modules over, say, bialgebra? The category of modules over bialgebra, you can consider just the category of usual modules. So you just ignore the bialgebra structure and consider only the algebra structure. So if you have A, with bialgebra, I don't know. So we can consider A modules, just ignoring the coalgebra structure, just thinking about the usual algebra. What the bialgebra structure gives you? I'm saying that it gives you monoidal structure on this category. Yeah, so if A is not commutative, then in general you don't have a nice monoidal structure on a category of A modules. M, so N, so you can't really tensor it over if it's not commutative. If it is commutative, you can tensor it over A, but this is not the thing that you want to do. You want to tensor it over C. And then we want to give a structure of a module of a module on this. So naturally you have a structure of A times A. But you also have delta. So you can restrict this model or pull back the model from this algebra to this algebra. And this we find to be M plus N in the category of A modules. So this gives you a monoidal structure of the category of A modules. Let's do example. The example that we like is C of G. And but now let's take so let G be a finite group, and let's take the convolution, like how do you call it? The convolution structure on C of G. This is the group algebra. Yes. So you probably know that this group algebra, as the category of models of the group algebra, is equivalent to the category of representation of solution. You know this theorem? Give it an example. Okay. So do you understand?
G is fine.
G is fine. So do you understand both sides? You can do it for not finite, but then you need to be careful with take finitely supported functions. So this is so if G is finite, representation of G, you know it. Yes, it's action of G on the vector space. Okay. And morphism of representation, linear maps that preserves the action. And this is a group algebra. So its elements are finitely supported functions on G, just functions of G. G is finite, and the product is convolution. And now I claim that modulus over this algebra is the same like representation of this group. Why? Because each time you have a model of this algebra, you can just say, okay, each element of the group give you delta function in a point, so it's also so you have functors of this direction. What about the other direction? Okay, each time you have a representation of this group, so you know how delta functions here should act. And then you know what any function should act because any function is a linear combination of delta functions. So these two categories are equivalent. Now in this category, you have tensor product. If you have two representations, pi and tau, you can have the tensor product. Not tensor product over G, there is also such a notion, but just tensor product over C. And this tensor product will have a natural structure of representation of G from left side and from the right side of G acts on this. And this gives you a structure of representation of G with respect to the diagonal direction of G. That's G acts on C on. And this gives you a monoidal category structure on this category. And this exactly is the monoidal category structure that comes from this whole algebra. That here you take involution and this component. This stupid component. And this exactly the restriction to G. the diagonal. Those are so it makes sense that if you have something which is analogous to group, you want it on the category of models of it, you will have tensor structure. So we discussed it when we formalize the Tanaka theorem, that if you have so the basic example of symmetric monoidal category is representation of an algebraic group. Here it's finite group, okay, it's also a special case of algebraic group, so representation of finite groups is also an example of tensor category. So representation of Hopf algebra is example of monoidal category, but it's not necessarily symmetric. And why it's not symmetric? Because okay, here we have to be careful, but here it's not symmetric because the co-algebra, sorry. What needs to happen in order to be symmetric? I think the co-algebra structure should be commutative. So if the co-algebra structure is commutative, you see, then this thing is symmetric because this method doesn't change when you change the order of A. Now, another thing you can do with Hopf algebra is a dual picture. You consider comodules over the algebra. So what is comodule? First, we discuss what is a module. Module of an algebra. The morphism from A tensor M. So, comodule is a morphism from M to M tensor A that satisfies some relation that are very similar to associative. So if Hopf algebra is coalgebra, you can consider the category of comodules, and then on this category you can get a monoidal structure that will come from the multiplication structure on the Hopf algebra. I will not spell it out now, but you just dual to the picture that I described. And this picture is probably better and better compatible with algebraic groups. So each time you have Hopf algebra of each time you have an algebraic group, then it is commutative Hopf algebra, but not commutative. So comodules over it will be just representation, algebraic representations of the algebraic. Here, why comodules? Because each time we have algebraic group G. So what does it mean if we have representation of G? It means if we have a map from G times B to V. So this does not give you a map from O, B, G, tensor V to V. You don't have an algebra, a model structure of a algebra. But you do have a map from B to O of G. Yeah, that's it. Each time you have vector in V, and now if you have element in G, you can act with this element on your vector V. So you get a function from G with value in V. Function from G with value in V. V is exactly element in this tensor form. So representation of a group, it's module over the Hopf algebra of regular functions of the group. So it does not care completely about the algebra structure on of G, only about the core algebra structure. You have to define what is representation, you don't need to know the algebra structure. But to define tensor product of representation, you need to know that. So if you have bialgebra, you can always use one structure to define category, modules or comodules, and the other structure to define monoidal structures. Okay, and maybe the first. Okay, maybe I will go to the next step now. This was about bialgebras. What about Hopf algebra? What the Hopf algebra gives you on the category of representations of the algebra of the coalgebra. Any guesses? What inversion of the antipode can give? So do you know the notion of dual representation? If you have group G acting on space V, then it also acts on the dual space of a function. And maybe the first presentation, I think we discuss it, is to write that the action is just will be pi star of G on the function of phi. on a vector V. So the first notation, which is wrong, will be to write P of G of. And you know that this is wrong. Naive way why it is wrong, because this will not be a group action. So product of 2G will go here to product of the other side, will reverse the product. And a better explanation why it's wrong, I should have explained it last time. If you have functions on a line and you want to move the function right, you want to move its graph to the right and not the graph to the left. So it means that the variable you have to move to the left. So the correct thing is so you see that in order to define duality, you need the notion of inverse. And in order to define, so now if you have Hopf algebra or bialgebra and you have finite dimensional representation of it, you cannot really define a duality. Well, you can try, but it will not really work. Yeah, if you have algebra A and module M over A, they find dimension over C, so you can consider M star. But M star will not have an action of the algebra A. Will have the action of the opposite algebra A. Because in A you don't have inverse, yes? So you can say A of phi is equal of phi at point V is equal to phi of A. This is correct definition. You will give some object here and star, but this object will not be a model. It will be a right A model or a model over A. But I will fill the name now. Let's call it lambda. But if you have antipodes, then you can redefine. So here you can write phi of A. Now this is the correct notion of duality inside the category itself. You can start with A model and get new A model. If A is if you have I, so if A is Hopf algebra, so it has algebra structure, coalgebra structure, and antipode, so the category of A models going to have what? And so the category of finite dimensional A model will be rigid. Of all A models, it will not be rigid because the duality will be kind of weird, but it will be here. It will be.
So, can I just get something clear? So, if we have a Hopf algebra, we can consider the modules of that algebra. Then all these structures allow us to get tensor product of modules and star and do all.
Yeah, but more specifically, the coproduct give you tensor product on models, and the antipode give you product. And if you also can reverse this picture. You can, if you have Hopf algebra, you can consider the category of comodules over this algebra. Then the product give you tensor product of comodules, and the antipode give you one. So you have to be a bit careful when you say duality. So if you just want some weak kind of duality, or remember that we discussed the weak kind of duality, like in vector spaces, then you can consider all models. But if you want the strong duality, the one with all the axioms that we said, and then it has to be, then you have to consider finite dimensional. Otherwise, B star star will not be endomorphic to B, so no. I didn't think about it, but it seems that automatically for any Hopf algebra, you automatically have pivot. So this comes down is endomorphic to B, it's dimensional. So you automatically get this additional pivot structure. Okay, what about braided structure? This is not so much. Hopf algebra, modulus of a Hopf algebra does not have to be braided category. If you have braided structure on this category, it just gives you some additional information, and specifically it gives you some element of 8 and below. Now, I don't know the details and I don't want to go into details, but I do want to tell you the words, so when you will see them, you will not be surprised. So if you have braided structure on your Hopf algebra, it's just equivalent to give some element here in A times A that satisfy some conditions. Like because the braided structure satisfies some conditions, the braid axioms, etc. So this element is called R matrix. So if you see the word R matrix in the context of the category, we know this is the element in A times A that satisfies these conditions. And the conditions that it satisfies called the Young-Baxter equations.
The what?
Young-Baxter equations. So if you see these two words, don't be too afraid. So Young-Baxter equations, just set of linear tensoring equation, whatever, on this element that ensures that it gives you a braided function. So there is a notion of braided Hopf algebra. So it's a Hopf algebra with R matrix, and R matrix is an element here that satisfies the Young-Baxter equation. Okay, so in the next hour, I will try to give an example of Hopf algebra. Maybe before this, I can say something this hour. So we have analog of Tanaka theorem for Hopf algebras. What does it mean? It means that if you have, say, braided monoidal category, probably even just monoidal category, maybe even not rigid, just a general monoidal category with fiber functor, then it's always equivalent. No, this is not correct. So let's say rigid monoidal category with fiber functor, it's equivalent to the category of modulus, finite dimensional modulus over some Hopf algebra. And if the category is also monoidal, then this Hopf algebra is also monoidal. So this generalizes the Tanaka theorem, because Tanaka theorem just put additional condition on the. So I said category of models, and I was wrong. I should have said category of commons, like before with algebraic groups. So we said the category, the tensor category, tensor symmetric category is equivalent to the category of modulus of representation of a group G, but this is exactly co-modulus over the algebra of regular functions. So it should be co-modulus, and the monoidal structure is given by product, and the duality structure is given by the antipode.
Please remind us what is the
Tanaka theorem says that if you have, I think it's 7 words, rigid, monoidal, symmetric, then abelian category, symmetric abelian, you can say it's tensor, with fiber functor, then the category cancels the collection of these guys. So let's start with start formulation. This category is equivalent to the category of G modules when G is algebraic.
what you're saying?
So if you erase the word symmetric, then when H is Hopf algebra. And you take care of problems. And you see that this one this theorem generalizes the previous one because it needs to do some work to deduce from this previous one. It makes sense because if you erase the word symmetric, so you have here a Hopf algebra. But now when you put the word symmetric, it gives you some condition of the Hopf algebra, and you see that the condition, in fact, is that it is commutative, so it's a regular functions on for algebraic. Because H module finite dimensional. answer before finding it. But otherwise it's not okay. So you can erase the word symmetric and then you want to also about yes. So what you actually will try to do is to find the example of such category, with fiber functor, and then we will know that it has to come from some of algebra, and since it will not be symmetric but only braided, this of algebra will not be not commutative and not common. And 15 minutes break.
באיזה תחום הם משתמשים באלגברות רוב?
זה קצת תחום בפני עצמו, אבל אני רוצה קודם כל לגדל שם מה זה הגדרה. יש לה שימוש מילים. איפה אני טיפול? פה בביטול גם. כן, הוא אנטי יותר מופיזם, כאן לאנטי לא דבר. So, איפה משתמשים באלגברות רוב? זה תחום בפני עצמו, אפשר לחשוב על יותר הכללה של חברות אלגבריות. נראה שבאמת מוטיבציה באה ממכניקה קוונטית, אז איך הכל זה קשור למכניקה קוונטית? היא לא באמת פרובילית, במכניקה קוונטית, אבל אני יכול להגיד איזשהו קשר. יש לנו את חוג, בפיזיקה קלאסית יש לנו את המרחב קונפורציה, מרחב הפאזי, שנקודה במרחב הפאזי אמורה להתאים מצד אחד מתאימה כאילו לתנאים התחלתיים של המערכת שלנו, אבל בעצם מכיוון שהכל אפשר לדבר, ברגע שאנחנו יודעים תנאים התחלתיים זה בעצם גרסה של המציאות. ואז כל שאלה שאנחנו שואלים על המערכת היא בעצם נותנת לנו פונקציה על מרחב הפאזי. בכל מצב של המערכת אני יכול לשאול מה הערך נאמר של השאלה. אז זה נקרא נצפה, ויש לנו את אלגברת הנצפים שזה פונקציית המרחב הפאזי. והיא כמובן אלגברה קונסטיבית, כי זה פונקציית המרחב. אפשר להכפיל אותה. ואז הטענה במכניקה קוונטית שזה לא עובד ככה, שזה לא נכון לתאר מצב של מערכת כנקודה על המרחב הפאזי. אלא במקום זה מתארים מצב של המערכת כאנדומורפיזם של איזשהו מרחב הילברט. עכשיו, מצב של מערכת כווקטור באיזשהו מרחב הילברט, יש קשר למרחב הפאזי, אבל זה לא חשוב. ואז אומרים שנצפה זה אנדומורפיזם של המרחב. שזה קצת מוזר, כי אני רוצה לשאול מה הערך של הנצפה, אז הייתי מצפה שאני פשוט צריך להציב את הוקטור לאנדומורפיזם. אבל אני לא אקבל שום דבר באנושמות, פשוט וקטור אחר. אז מה, אני אומר במכניקה קוונטית? לא, אני לא מציב את הוקטור לאנדומורפיזם, אני מפרק את הוקטור הזה לוקטור עצמיים של האנדומורפיזם. ואז, אם הוא במקרה יוצא וקטור עצמי, אז זה הערך של הנצפה. ואם הוא לא וקטור עצמי, זו קומבינציה של וקטורים עצמיים, והמשקלים, או ליתר דיוק ריבועים שלהם, אומרים מה הסיכוי שזה יהיה הערך. זאת אומרת שאני לא באמת יכול לדעת מראש את הערך של הנצפה עד שאני מבצע נדידה. וביצוע הנדידה זה בדיוק היטל לנצפה, כן? היטל לוקטור העצמי, לאיזה וקטור עצמי, איזה שיוצא. אבל יותר סביר שזה יהיה לכזה שמופיע בקודם גדול מאשר כזה שזה מופיע בקודם. אז זה הרעיון שלו. להגיד שאני מבין אותך, אני לא יכול. ואז, אם יש לנו שתי נצפים שמתחלפים, אז מה זה אומר? זה אומר שלשניהם יכול להיות משמעות בו זמנית. אפשר לנסות אותם ביחד. זאת אומרת, יש וקטורים עצמיים שהם וקטורים עצמיים משותפים. אז אם כל הנצפים בעולם היו מתחלפים, אז כל המערכת, כל הרעיון הזה שלנו, הפרקטורים מתחלפים.
כן.
אז כל הרעיון הזה היה מיותר לגמרי. הייתי אומר, בוא נפרק את הכל לוקטורים עצמיים שיהיו עצמיים לכל הנצפים בעולם. ואז אוסף הוקטורים האלה היה בעצם המרחב הפאזי האמיתי שלי. כל נקודה, כל וקטור כזה אומר מצב אמיתי שיש לו ערך אמיתי. ואם אנחנו רוצים לדבר על מצבים שהם מעורבים, אז גם במכניקה קלאסית אפשר לדבר על מצבים שהם מעורבים, כן? אני גם יכול להגיד שאני פשוט לא יודע איפה האלקטרון. הוא נמצא איפה שאני לא יודע איפה הוא. אז אני אגיד שיש לי איזושהי התפלגות. ואם זה היה המעבר ממכניקה קוונטית לקלאסית, אז לא הייתה לו הרבה משמעות, כן? בסדר, גם בקלאסית אפשר להניח שיש לי מידע חלקי ולעבוד עם תורת התפלגות. זה לא החידוש המרכזי שלנו. והחידוש המרכזי הוא זה שאנחנו יודעים שיש מצבים לא מתחלקים. זה אומר שאין להם וקטור צבי משותף, זה אומר שאם המצב שלנו הוא טהור מבחינת אחד מהם, זאת אומרת שבאמת יש משמעות לאחד הנספים, אז זה אומר שלשני בהכרח לא נותנים. שהדוגמה הקלאסית זה קום בטנא, אני יודע איפה נמצא האלקטרון, ואני לא יודע שום דבר על המהירות שלו, ואם אני יודע קצת על איפה הוא נמצא, אז אני יכול לדעת קצת על המהירות, ובהתאם לכך. אבל בכל מקרה יוצא שהשחקן החשוב במכניקה קוונטית זה אלגברת הנספים. והיא מחליפה את השחקן החשוב במכניקה קלאסית, שזה אלגברת הפונקציות על מרחב הפאזי. עכשיו, אלגברת הפונקציות על מרחב הפאזי, אני יכול להגיד שסתם אלגברה קונקטיבית. כל אלגברה קונקטיבית היא פחות או יותר אלגברה פונקציות על משהו. תלוי בסטינג שאני עובד, אם בסטינג בטופולוגי, אז אלגברת צי כוכב היא מותגים צי כוכב בפונקציות על מרחב טופולוגי, ואם בסטינג אלגברי, אז האלגברה נוצרת סופית זה תגריה אלגברית. אבל בכל מקרה, אלגברת פונקציות, אלגברה קונקטיבית וגיאומטריה זה די יותר דבר. ולכן, אם אנחנו רוצים לעשות משהו שיגביל את זה, אבל נתאים למכניקה הקוונטית, אז אנחנו צריכים לדבר על אלגברות לא. אז זה הייתה המוטיבציה לדבר על אלגברות לא קונקטיביות, אבל לחשוב עליהן כאילו הן כן, כאילו הן פונקציות על משהו. ולנסות לראות מה שורד מהתורה, למשל, נגדיר מה זה חבורות. חבורות שהמרחב עצמו הוא מרחב לא קונקטיבי. אין באמת מרחב, אבל יש רק אלגברה של פונקציות עליו והיא לא. עכשיו, זה לא כל הסיפור, יש עוד אלמנט בסיפור הזה, שטוב, קשור למה שדובר על אותה ההסקה. זה קבוע פלנק. כן, אז אנחנו יודעים שבמכניקה קוונטית יש קבוע פלנק שבעצם אומר עד כמה היא קוונטית. קבוע, אז לא אפשר באמת לשאול אותו, ואנחנו יודעים שבחיי היום-יום אנחנו חושבים עליו כאל משהו מאוד קטן, קטנה כאילו תיאורטית לגמרי אין משמעות לאמירה שהוא קטן, הוא עם יחידות, תלוי מה היחידות שאתה בוחר, אבל בקנה מידה של יום-יום הוא מאוד קטן, ולכן גם המכניקה קוונטית היא מאוד דומה לקלאסית, לא רואים אותה בחיי היום-יום, עד שאנחנו לא מתחילים להגיע בקנה מידה שמתאים לקבוע. אז מנקודת מבט מתמטית, מה שהם אומרים שבוא לא נחשוב על קבוע פלנק קבוע, נחשוב על פרמטר. וכשהפרמטר הזה שואף לאפס, המכניקה הקוונטית צריכה להתנוון בחלוטין לקלאס. ואז, מה שאנחנו באמת רוצים, כשאנחנו רוצים לעשות קוונטיזציה לאיזושהי מערכת, יש לנו איזושהי אלגברה קוגניטיבית, ואנחנו רוצים לעשות קוונטיזציה, אנחנו רוצים לעשות מערכת חד פרמטרית של אלגברות, שבפרמטר של אלגברות לא קוגניטיביות, שכשאתה מציל אפס, אתה מקבל את האלגברה. כשהוא מאוד קרוב לאפס, זה יהיה מאוד קרוב לאלגברה. וזה בעצם מה שאנחנו נצטרך. כל הרעיון בחבורות קוונטיות זה, אוקיי, יש לנו חבורות אלגבריות למשל, או אלגברותי, או לא משנה, חבורות מדות, אנחנו רוצים לעשות להן קוונטיזציה. אנחנו רוצים לשים אותם במערכת חד פרמטרית של אלגברות הופ, של הפרמטר שהוא אפס. זה הדבר הזה, עכשיו זה לא שיש רק אינפורמציה אחת, הם שמים מאוד תנאים, ובסוף הם בוחרים איזושהי אינפורמציה שהם אוהבים יותר מאחור. זה מהפעול בחבורה. אבל יש עוד שימוש אחר, שהוא דווקא קלאסי לגמרי, אולי נדבר בשחר, אולי אפשר לעשות אותו, זה בתורת ההצגות של SR. שמתברר שאפשר במסד מסוים לקודד את כל תורת ההצגות של כל ה-SR ביחד, בהופ פייל ג'בר אחת. אבל היא דווקא, כן, היא דווקא קומולטיבית. שימוש באופן גבוהות וכאילו ריק. אני חושב שהיא גם קומולטיבית וגם קוקם. ובעצם אפשר להפיין את זה ככה, היא סלף דואל, קונטקטיבית וקוגניטיבית, זה שנגיעות הרגילות. ואז יש חברות אחרות שהם עושים להם תורת ההשגות וגם מנסים להראות הרבה חברות ביחד, אז פתאום מקבלים גם אנטיבות כזאת. היא לא היחידה, אבל היא האובייקט התחילי, כאילו היא האוניברסלית, וכל האחרות קיבלות כמו סכום של הרבה אקטיב שלה. ואז אפשר לעשות תורת ההשגות של חברות אחרות, לעשות רדוקציה לתורת ההשגות של SM, שוב בגלל שגם היא מגדירה הרבה פעמים בגלל שנגע את כל עצמו.
זה קשור לעשות קטגוריה.
לא, לא, זה נגמר בסוף.
אז אתה פשוט חושב שהוא יספר את זה.
לא, שחר.
שחר, כן.
לתרגול, הוא פשוט תוכל לדוגמה להפחות. אני קודם שאלתי אותך אם עכשיו יש לנו ממש מעט דקות על הדיבות, אם אתה רוצה אחרי השיעור.
לא, באופן כללי, אני
מבין שללמוד תואר ראשון בין הרצאות של קורס זה לא ממש פרקטי, אבל להכיר אפשר הרבה דברים, אתה יודע. יש להם גישה אמריקאית.
אני באופן כללי נרשמתי לקורס הזה, כי קראתי את הסילבוס והכתוב שם. צריך בייסיק גרופ תיאורי, אוקיי, זה יש לי. וכל השאר הוא צריך חלק מהדוגמאות.
אמרתי כזה, 60% מהדוגמאות, 50% מהדוגמאות.
לא, זה ספציפית השתי הרצאות האחרונות היו קצת קשות.
כן, איכשהו קפצנו עכשיו ברמה, זה לעומק, כן.
זה פשוט יותר דוגמאות, פחות
לא, אבל הרצאות האחרונות היו גם את התיאוריה, אבל התיאוריה היא יותר עמוקה של
כן, אבל
התגובות מונידליות, שהיא שואבת את כל האינטואיציה מהרבה דוגמאות, זה לא תיאוריה כללית שאפשר להפעיל את כל דוגמה בעולם. יש לי גישה אמריקאית, אני הייתי לשוק פעם ראשונה ממנה, נראה שבעצם מה שהם עושים בארבע שנים באוניברסיטה, זה הם מלמדים את הבן אדם לא להבדיל בין אני מומחה בתחום ובין אין לי מושג מה מדובר. הם איכשהו לא רואים את זה בשתי גישות האלה, ואז הם מספרים לנו הרבה דברים רק ברמה של כותרות, ומכאן שזה כל מה שהם מספרים, אז בסוף לבעיה נמצא רושם שככה זה עובד, אתה יודע את הכותרת, אתה יודע את הדבר. אז מצד אחד זו גישה רעה, אם שימו אותה עד הסוף, אבל מצד שני כאילו כן אפשר להכיר דברים בלי לדעת על העומק, וזה כן יכול לעזור, חשוב לדעת מתי אתה יודע העומק ומתי לא. אז ברמה הזאת כן אפשר ללמוד תואר ראשון, זה סוף. לא, לא, זה 10 שנים. ואני חושב שיש דרך, לא יודע, כן נתקל בזה לי זה עוזר שאני יודע על מה מדובר לפני שאני יודע מה זה, כן?
אז עכשיו ממשיכים עם זה, וההרצאה הבאה...
אני רציתי כבר עכשיו להתחיל לדבר על, עוד לא קטגוריות נגזרות, אבל לגזור פנקטורים, פנקטורים וכו'. זה לא אספיק בגלל שאני נראה לי את הפיגוע של השעה הראשונה. זה, אבל אולי אני אספיק לפתח עוד משהו. אני כבר די קרוב לסיום, אני מתכוון, לא יודע, תמיד שטוב, שלא מתכוננים למצוא בסיום שטוב. אני כאן כאילו לא רוצה לספר לכם את כל האמת, כי שוב, קטגוריות מנואידליות זה מצדיק קורס מסוים, כן? אני רוצה לספר עוד דברים, אני לא יכול לספר. אני באמת, כאילו, אני זוכר שלקחתי את הקורס, זה ריאלי, אבל אז לא ערכתי אותו מספיק. עכשיו אני כמה זה נושא יפה. גם אז לא הייתה קיימת התוצאה הזאת על הקטגוריה הבלית. אני רוצה לפני בלית וכל המקום. טוב, רשמתי לעצמי דברים. לא רשם. אני כתוב פעמיים, לפעמים פעם כתוב את זה. נכון. רגע, רק פה למשל, אין ברכה. אולי יותר מרבע שעה. So, now I wanted the door. So I wanted to give some example of. So we already had an example of rigid monoidal category, which is rigid monoidal braided category, which is not symmetric, which was free. The free thing, so now we know free tangled and not just tangled. And so we can say we're happy, but because this is not does not have fiber function. So it's not. In fact, it's not even additive. Yes, just strings. But we can make out of it additive. Just take the bit of pen, and then it's not have fiber. Does not have fiber. So what we will do, we'll impose some additional relations that will make to have fiber. And maybe you remember that last time, if we wanted, last time what we did when in the symmetric world, we impose additional relation that the loop is n. And then, we say, okay, the loop can be some number t, and then it was not a billion, so we take the cubization, and then might be a billion, unless the number t is integer. But if the number t is integer, maybe it's not a billion, but it's kind of the most interesting situation, because then we can get representations of algebraic group here. And now we want to do the same in the non-commutative world, but we need more relations. So here are the relations. I don't know how to justify them. I copied them from Wikipedia and other places, but then I don't know what is the intuition behind it. So we choose two parameters, q and n. And n is the analog of this n. It can be an integer, but in principle doesn't have to be an integer. And then we do two relations. One relation is this one. What do we mean by this? So this is an element, this is a morphism in our category, the breaking. This is the implicit dividing, this is the difference, and this is the identity. So we don't ask the category to be commutative, so we don't want the, sorry, the category to be symmetric, so we don't want this divide to be equal, but we want the difference to be constant times identity, and we normalize the constant in this one. When q is a parameter, and you see that q is equal to 1, you get 0, so is equal. And another relation, u to the n minus q to the minus n, and a q minus q inverse. This. Yeah, so we would think the dimension should be n, but it doesn't work like this. Yes, and if the category is not symmetric, then you don't expect the dimension of the standard object to be an integer number, even if it's nice category of representations, etc. But you do expect it to be. So what happens when you plug in q equal to 1? So the short answer is nothing happens, it's totally fine. But the longer answer, you know how to compute with n equal to 1? Maybe.
N is equal to 1.
Well, q is equal to 1. I hope I'm correct. I hope it should give you n. If it does not give you n, then you probably should change q with square root q and then maybe it will be 2n and then it will be change q to square root. Yes, so you can check it. So it takes the limits and q tends to 1, it becomes 0.
So what did we try to do?
I want now to define a category, which will be a quotient of the frame time category, but will be nicer. So it will be a billion at the end. We have to make it a billion chunk to be a billion, and you want it to be and it will have fiber function. Okay, so I just impose some new relations, and they don't really know where the relation came from. So these are the two relations, and now because how I understood that I was mistaken, this thing it's not trivial, it's a twist, so it's a non-trivial ribbon or whatever, or twisting the category. So it looks from a topic to a string, but it's also like a string, but it's a twist the topic. And then it should be q to 1. And again, when q is equal to 1, then it is 3.
Everywhere you mean that you have to, you also multiply by the.
Wait, what?
No, never.
So what happens? You start with so you now you can define a new category where objects are again arrows up and down, and another right for framing, but it always the right so we can know it. Morphisms are frame tangles. Modulo these relations. And each time when you see one of these things, you can replace it with the other, but with this price. And each time when you see this thing, you can erase it, and each time when you see this thing, you can untwist it, but with the price. When I say it's, of course, I need to take the linear span of all tangles, and then I can push the relation. Because before, it doesn't, I can't push the relation before. So what you can see in this category is you can untangle anything, yes? Because, okay, loops you just erase, twist you just erase, yes, because of this, so don't care about them anymore. And now you just have crossings. So usually if you have link or not or whatever, you can just try to tear it out, yes? So, למשוך, until it just straightens, but then you see that you need to make many crossings disappear. But now you can make them disappear. Each time you want to make crossings disappear, so the idea is that you could have made it disappear if it was the correct direction. Each time the correct direction is different, yes, but each time you have something that doesn't let the go, so what can be? What can be? It can be something like this. It doesn't let go. But if you will change one of those intersections, then it will let go. So you just use it axiom in order to change it, and then get another thing which is easier to untangle because you just erase the intersection. So even less intersections, so by induction you can untangle. So you can use this relation to untangle everything. So on the level of morphisms, the dimension of the space of morphisms is kind of small. It's as small as the as morphisms in the Bauer category. So we only have permutations. But the in fact, it can be even smaller, yes, because it might be that you can untangle the same thing in two different ways and get two different answers, and then give you more and more relations. So this does not happen. It's not your this does not happen. So you can untangle everything, but basically in a unique way. So the dimension of the space of morphism is rather small, but not too small. And what do you get? So you get a category. Now this category is additive, because they already took the linear span and they also need to add direct sums. Now you can take its coordination, or idempotently closed it. And so I add all the kernel idempotents. And then I get covariant. But it's still not the not an abelian category. But now the miracle happens. You have the notion of dimension. What is dimension? It's any object you can consider its dimension by like here trace of dimension. Yes. And the dimension going to be so here the dimension is some number which is not zero. but when you consider general objects, which might be like a direct summand of some complicated combination, so for example, the symmetric powers, the anti-symmetric power, we have lots of objects, and some of them will have dimension 0. And like we saw before in the situation of GLM, so if we instead of all this, so if here we just put 0, here we just put n, and here we just put 1, and this we put times this. And so yeah, this I don't put times anything because it times like the identity morphism of the identity element. Here it's times the identity morphism of the generating element. So if you put you go to the classical case and you see that you still have like lambda n of the generating object of the point. Here you take the point, you take this tensor power, then you have action of Sn, and then you can take lambda n, which is direct summand, and it's defined in the computation. And this lambda n for large n, and for n which, oh, maybe not n, k. If k is larger than the dimension of the standard object, or larger than the loop, then it has to be 0. We will discuss it because we know compute the dimension. We see that the dimension of the generating object, which let's call it d, or in this case it's n, so n times n minus 1 times n minus 2, etc., divided by k factorial. So if you go over the dimension, you get 0 the product, so you get 0 dimensional object. But this object is not 0 in this free category, yes, because we didn't ask it to be 0, it will not be 0. But it is 0 in the category of representations of GLM, because this is just the exterior point. It is 0 if you have a fiber functor. So if you want to have a fiber functor, 0-dimensional objects have to be 0. Because fiber functor preserve dimension and vector spaces have 0 dimension. Yeah, now we're confused about the fiber functor. Or yeah, okay. Now I understand that I didn't formulate it correctly because I don't know what fiber functor means. Because the dimension here is not integer. So it doesn't really make sense to start with braided category, which is not symmetric, and then make fiber functor to something symmetric. So I need to check. I don't know, but let's ignore it. And what do you get? And so you need to take this category and factor it by all the objects of 0 dimension. So what does it mean to factor it? There is some notion of quotient of a category by tensor subs. So by a tensor category by its subcategory. So the subcategory should be something which is analogous to ideal, and then you can find quotient. I think it's just the usual quotient by a third subcategory that we probably discussed before. But now we have to find the monoidal structure, and you can. And then the magic happens that this is abelian. And you see that if Q is equal to 1, this is not just a abelian category, it's just a category of representations of GLM. And if n is not, if Q is equal to 1, and if Q is not equal to 1, then we'll call it the category of representation of GLM. And indeed, it is a category of representation of certain Hopf algebra, of core representation, in fact, of certain Hopf algebra that is called O of GLM. And this was called what is called quantum GLM. So what is the general philosophy behind quantum groups? So you start with some nice algebraic group, or you can do it in different settings. So just basically two main settings: the setting of algebraic groups and the setting of Lie algebras. So in the setting of algebraic group, you start with algebraic group G. You have OG. How many would better to write like this? So you start with algebraic group, and then you put additional parameter to the algebra. So instead of considering regular functions, you have one parametric family of algebras of of Hopf algebras that for q equal to 1 give you the Hopf algebra of G, and for other q give you other things. So you could have, in principle, have many one-parametric families. So quantum group is not just arbitrary one-parametric family. For any algebraic group, is some, or reductive algebraic group, whatever. It's some very specific one-parametric family. I don't know how to characterize it by its properties. So I don't. Not only I don't know the construction. So the construction is so somewhere it's horrible formulas, but there are
Of this
what
version.
of this. And so there are ways to. So yeah, I saw the horrible formulas, but I don't understand what they mean, and there's probably a way to characterize it by less horrible formulas, but they're still kind of complicated. So I don't fully understand the idea. But in the case of GLN, the nice thing that you get something which is almost free. So it's free, subject to this condition, and subject to the condition that zero-dimensional object has. And then you get something free, and it turns out to be a billion. And so there are two, like in the literature, you find two versions of quantum group. This is the less popular version. And the more popular version is the algebraic version, which is the formation of the universal enveloping algebra of G. So this is sometimes called quantum universal enveloping algebra, and this is called quantum algebra of regular functions.
Okay, so this is going to be the representations
Of this? Oh, sorry, of co-representations. They're going to be co-representations of this.
of
and-
GLN.
Of G.
Okay.
Yes. Here I thought G, and I got the G. But these two versions are so this is the Lie algebraic version, so it means that for q equal to 1 you go to the inverse enveloping algebra. So here for q equal to 1 you get something which is not commutative but co-commutative. Here when q is equal to 1 we get something which is commutative but not co-commutative. And for general q you get in both cases something which is neither commutative nor co-commutative. And those guys are dual. In what sense? So for example, in what sense usual or is dual to dual? So if you consider only fine-dimensional representations, okay, it's also not completely correct, but fine-dimensional representations of O of G, sorry, fine-dimensional comodules of O of G is exactly fine-dimensional representations of G. And this is more or less the same as fine-dimensional representation of the Lie algebra of G, which is the same as fine-dimensional representation of U. Why I say more or less? Because it's not always true. It's true for simply connected.
Wait, so
Simply connected.
G is a Lie group, but also an
Algebraic.
algebraic group.
So G is algebraic group. Algebraic group also has the notion of a Lie algebra of algebraic group. Why? Because what is Lie algebra of a group is a tangent space. Yes. So in algebraic group you can also do tangent space. You can do geometry, algebraic geometry as well as most geometry convention. So tangent space of the unity also has a structure of the algebra. And the algebra is the same notion for algebraic and non-algebraic group. The only difference is that you can do algebraic groups over any field. The groups usually need to hold see. If you negotiate enough, you can do KP. More or less, this is well, it's so. Representation of algebraic group and representation of Lie algebra, it's almost the same. And so the group should be simply connected. Otherwise, this will have more representations. And here also, co-representation of these Hopf algebras, of algebra and representation of this algebra are almost equivalent, or in many cases are. And in the case of GLN, it can be described as this universal properties. Just we start with strings and put conditions and then kill all the object of the ordering function. Now we can ask what will happen if you will take here n, which is just a parameter or any complex number, and then all the theories that we had before for GLN or classical GLN is done. We'll take a bit later, but done also for the quantum case. So if n is a parameter, abstract parameter, then this category, after you take the cohabitation, is already abelian. If n is a complex non-integer parameter, then this category is abelian. And if it's integer parameter, this category is not abelian. And then you can decide what guys to kill. So you can take its quotient, which will be abelian. It's an infinite abelian quotient, but also it have another abelian category. So all the stuff.
Instead of GLN,
What?
what do you get instead of GLN?
Here also we can ask what. So you get Hopf algebra. You don't get actual book. So OQGLN, it's a Hopf algebra. And so it's not actually function of some group. You can describe you can describe it with generator and relation. So usually it's easier to do it in this language. And this language is just as a vector space, it looks like the inverse of Hopf algebra. It's G plus G times G plus G times G times G, etc. But the relations are different. So it's generated by G. So the universal Evocolocking algebra is just algebra generated by G with relations that commutator is the usual commutator. And here the relations are different. And the coproduct structure is different. Static. Okay. So maybe the last thing I want to say about monoidal categories is that we did define the notion of product in any category. And if a category has a product, then this product gives you a monoidal structure. And such a monoidal category is called Cartesian monoidal category. And in principle, you can say that maybe it is an additional structure, like the associator and the grading and whatever. And they're kind of non-unique, but in fact, it's not really additional structure. So Cartesian monoidal, if you have product, then there's only one reasonable structure. This is called Cartesian monoidal category, which is like category. So I think it's enough for monoidal categories. You have any question about it? I want to go to the ref. So first of all, I want to go back to your question about shifts and give an example of morphism of shift, which is onto a morphism of shifts, but not onto the morphism of pressures. And here, this is like manifestation of the fact that when is the objective function for shift by shift is not exact, and equivalently or more or less equivalently, that the function of global section is not exact. So here is a nice example. You have S1, and you have the sheaf of smooth functions on S1. Sections of on the open set is, and you have another copy of the same sheaf. And you have the derivation here. This is a shift, a homomorphism of shifts. It's not like a homomorphism of algebras or of modules over some algebras, but it is homomorphism. It's commute with restriction. If you have a function, you derive it and then restrict. You can first restrict and then derive the same thing. So how do you think? Is this map onto or not onto? It is on. But what I think of map of shifts, so as a map of per shifts, let's start. Is it onto a map of per shifts? is it. Does any function have a feature to how do you say feature to kind of help, you know, you have an integral, but you're walking over a circle, not over the line. Over the line, you know, any smooth function have an indefinite integral, even many integral and the C. Do you have indefinite integral here? זה לא שאלה קשה. לא, תנו לי משהו. Okay, what are functions on the circle? How you, if you want to discuss it in first year course, what you would say instead of saying function on the circle. Periodic function. So let's reframe my question in terms of periodic function. Oh, yes, so I want the periodic function will have antiderivative, but inside the space of periodic function. So I want the antiderivative, the indefinite integral of periodic function. So is it true? Sometimes is it true? The chance to be true? What? Equal, if it's constantly equal to 0, yes, but you need much weaker condition. What is the condition of periodic function? So its antiderivative will be periodic. Why is it not periodic? What happens when you can write the integral? Integral from 0 to x, compute the integral, and it's not periodic. How to measure how much it's not periodic? It's not so far from it. So we have f of t integral from 0 to x. I want it to be periodic, so I want to compare its value, say 0.0 and 0.2 pi. So period, say 2 pi. What is the difference? 0.0, this is 0. Yes? 0.2, right? The total integral of the entire circle. Now, if this is 0, then it will be periodic. Because any difference is going to be integral over a period, and f is periodic function, so integral over any period is the same. But the integral over a period doesn't have to be 0. Now, this map is almost onto it. The codimension of the image is 1. But still, it's not on the level of global sections. So just consider the entire S1. But now we don't consider S1. You want to take a small, then some open neighborhood S1, which is not the entire thing, which takes something smaller. Is this map onto here? Yes. Because you have antiderivative, and this is just an interval. You don't care that the values do not match. So here you have one value, here another, it's okay. So what does it mean for map of shifts to be onto? It means that for any open neighborhood here, or any U, and any section here, you don't necessarily have a per image, but locally you have a per image. So for any point in U, you have a neighborhood and per image of this section and this neighborhood. Now you can say, okay, we have the shift condition. If we have many per images, we can glue them together to one big per image, but this is not necessarily correct because you have to be able to glue them together. The per image is not unique. You need to choose a per image in some way, and then it's not necessarily compatible. So if the map is 1-to-1, then to be onto is just the same as to be onto the global level of the global section, because then you can use it. But since this map is not 1-to-1, it's not really onto. What's the kernel of this map? זה לא שאלה קשה. What is the kernel of this map? Constant functions, or this is a global kernel, but in general, for general open set, what's going to be the kernel? still kind of constant, but there is no constant functions does not form sheaf because it's not a local property. But locally constant functions is. So the derivative is 0 doesn't really mean that you're constant, it's just locally constant, which usually means you're constant. So the kernel of this map, so this is an exact sequence. So the kernel of this map is a constant sheaf, and the co-kernel of this map is 0, so it's exact sequence. But when you pass to global sections, and then you see that this is not my sequence anymore. And if this would be 0, then you would not see this figure. So the fact that this sequence is not exact after you pass to global sections has to do something with a constant sheaf of S1. Now, if you would work on R and not S1, then also the kernel would be the constant sheaf of S1. And then there would be no problem with the constant, it's a with the co-kernel. And the reason is that the constant sheaf on the line behaves better than the constant sheaf on the circle. And you see what is the reason, because the circle is kind of round, it's a non-trivial topology, so something is going on. And of course, like if you, so if the topology is kind of contractible, it doesn't really mean that everything will work nicely. For example, you can work on the plane, but still consider the same sheaf. So the sheaf of functions on the circle, but you consider it as a sheaf on the plane. Formally, what does it mean? That for any open set in the plane, you intersect it with the circle and just consider the functions there. So you will get completely the same picture because the kernel going to be not the constant sheaf on the plane, but the constant sheaf on the circle. And although the plane have like kind of trivial topology from multiple point of view, the circle have non-trivial topology. So sheaf on the plane still can have something non-trivial. And now this picture is very nice, but it's a bit like infinite dimensional. And yes, these sheaves are very big sheaves. So here is a version which is much cheaper, but basically the same idea. But instead of working with smooth function, we will work with functions on open sets. So we have two sets, U and V, which are two open sets of the circle, which look like this, like intervals, but with overlap. They cover everything and with some overlap. And then I can consider what do we want to consider? The constant sheaf on U. What does it mean, the constant sheaf on U? Again, it means that if you have any open set, you intersect it in U with U and consider local constant function. Plus the constant sheaf on V. And here you consider the difference. You can consider the sum also. The difference. And consider the constant, a map to constant sheaf on U intersection V. What does it mean? That if you have locally constant function on U and locally constant function on V, you can restrict them to the intersection and take the difference. And constant sheaf on U to the intersection with V means that you take any open set, intersect it with this intersection, and consider local constant function. And again, this is an onto map because you can locally, for any point here, find a small neighborhood such that you can present the function as difference of function in U and function. But globally, if you have constant functions in entire U and entire V, or locally constant in entire U means constant, locally constant in entire V means constant. So the difference has to be constant on the intersection. But there are locally constant functions on the intersection which are not constant. You can put 5 here and 7 here. So this is locally, this map is onto, but only locally, only at map shifts. But globally, it is not onto. Okay, it's not onto map of per shift, so it's not onto map on the level of global shift. And the kernel here also going to be what is kernel? We have pair of functions here on U and on V. You can intersect with open set, but you can see globally such that the difference on the intersection is 0. What does it actually mean? It's locally constant global function because locally constant functions are sheaf. So again, the kernel is going to be the same kernel. So I not claim that each time when you see the kernel, it means that the map going to make problems, so it will be onto the global section, but it's kind of good indication that you might have problems. Okay, so we saw now an interesting example of non-exact functor of global sections. And of course, this is not the simplest example, it's kind of interesting in topology, but you have lots of non-exact functors. You have tensor product, you have home, you have group invariance if the group is not finite or your field is a positive characteristic. You have group co-invariance. You have lots of functors which are not exact. And most of them will be exact from one side. So for example, global sections is exact from the left. 1 to 1 maps to 1 to 1, but onto does not map to 1. And now we have a function which is not exact. And you want to measure how much it is not exact. And this is the activation for the notion of functors. And we generalize special case of it's cohomologies, and there are many kinds of homologies, and group cohomologies, group homologies. Homologies or cohomologies is kind of symmetric from this point of view, just to pass to the different direction of the figure level. And so this is all working for now, at least for now, of this course in the setting of abelian categories. So there are versions for non-abelian categories, but are more complicated significantly. So I will not define now in general the derived functor. I would just list some wish list what I want from derived functor. So suppose I have a functor from C to D, and say it is left exact, just for simplicity. Not just for simplicity. Say it's left exact, so you can do the same for right exact. For functors that are not exact for any direction, it's much harder. I want to define what does it mean to have a derived functor? So it's left exact, so I need to derive it from the right. So Ri of f, it's also functor from C to D. So I want sequence of functors with R of f, and with the following point that each time I have a sequence, x, y, then I get such exact. So we know that this is exact because the functor is left exact. But I know that usually I cannot put another 0. But I want to have a map here, which should exist. Now now R1 of f of f is also a functor, so I already can continue it. One. Then I want something here. R2. Etc. Say to infinity, or sometimes you want a high enough derivative will be 0, and then no, 0 something. So in no sense this thing defines the notion of the derived functor, because even if your functor is exact, you can just come up with some stupid other functors and makes its map always 0. So I think it's possible to make out of the definition if you put some universal property here. So there should be kind of minimal postulates that you don't add unnecessary minimal possible thing, but I didn't find the reference, I don't know how to do it. And it doesn't really matter because we will just keep it when we will define the better notion of the derived functor when we can. But here is a recipe how to compute it in some cases. No. Maybe yes. Okay. I will do it very vaguely today. better next time. So suppose you have some objects which are good, which you kind of know that the right function are going to be zero for some reason. And then I claim that you can do the following procedure. If you have enough. You can take X and embed it to such a good object. And then you can take this. So this is not exact sequence. So okay, you can make out of exact sequence on X. But this is not a good object. Let's say you can embed it to another good object. And then you can continue. The co-kernel is not good, but we embed it to another good object. And so on.
This is some resolution.
Yes, but I didn't say what is resolution. Such procedure called a resolution of X. What does it mean? Well, okay, how it's related to X. So let's consider. So first of all, I claim that this sequence is exact. Exact sequence, the image equal to the kernel. The image here equal to this kernel, but here we choose an embedding, so we didn't change the kernel. And again, the image each time is equal to the kernel by construction. So what is actually called the resolution? Now we do some nasty change. We erase the X, which is kind of fun. So we go start with X. So that was all. Now this sequence is not exact. It's not exact here. The image is 0 and the kernel is X. So I don't remember whether I talked about it. If we have non-exact sequence, but it is a complex, so the square of the differential, the square of this map is 0, which means that the image is included in the kernel. So I can consider the cohomology of this sequence. So I can take the kernel modulo the image in each level. So here all the cohomologies will be 0, and here is the cohomology going to be X, because it's going to be X modulo 0. And this was called resolution. So if you have a nice complex with nice object, I don't say in what sense nice, and that all the cohomology is going to be 0 except of the first one, which is your object, then we say that this complex resolves your X. So you start with one object X, and then you kind of replace it with this horizontal thing. So you can say it's horizontal thing is much worse, because this was one object in this complex, but it's also better, because the objects in this complex are good. And then you do the funny thing. You plug in each of F to each of them. No, in each of them. Each of them into F. Now F is a functor, so it's map complex to complex, because map composition to composition and addition functor 0 to 0. But F is not exact functor. So it doesn't really map in exact sequence. So this is almost exact sequence, although it's not completely exact, it's almost exact. It doesn't map to exact sequence at all. So here you will have lots of cohomologies. The 0 cohomology is going to be f of x. Because because I feel exact from the left, so this part is x. And all the other going to be something. These are the derived functor of f applied to f. So this is very ad hoc construction, because I didn't say what is this good object. And even if I would say, so we can have lots of choices how to choose a good object. But under reasonable conditions, this construction actually gives you a sequence of functors that could satisfy this thing, and in a sense, kind of nature. So next time, we'll start. How many times did I go? No, ne? I think it's about citing. Citing. לחף בבלוגים. הרי דיברנו על פרשים על הקטגוריות ועל פרשים במטרופולוגים. זה כאילו יש מאוד שנים, אבל לא דיברנו על שיפים על הקטגוריות. ויש דבר כדי.
זה יכול להעביר אותה. זה לא שיש מבחן. שמעת על פול ברסלס, זה באמת כן. זה מתאר בדיוק את זה.